So, welcome to our meeting, interaction meeting for advanced analytics course. Um, there was some question in our last meeting about how the modular operation is coming up in of the examples of affine transforms, primitive affine transforms that are scaling. And there was a lot of discussion on how this can be written as a nested loop with a floor and a ceiling and so on. I thought about this a little bit more. First of all, I want to point out that if you use the operators like floor and ceiling, it's no longer a fine. So even that is not really a fine. And really, I mean that particular example. I mean, there are two ways to write that program, right? Either you could kind of split it into two different loops, and one loop is going only for even indices, and the other is going for all indices. Or you can merge them and use this modulus operation. And it's more of a pattern matching kind of a transformation, which actually converts an affine program to a non-affine, and then you can have a reverse pattern match that can basically converts a non-affine back to affine and things like that. So I mean, as far as I can tell, this is basically just a pattern matching thing, and I mean, need not necessarily fit into our fine theory and things like that. Okay, let's start with today's discussion, which is on the last remaining topics that we're going to discuss in this course, which for polyhedral transformations, and after that we're going to pick different topics, and that's pipelining and blocking. And over to you, Harsh.
Yes, sir. So I am Harsh Yadav. I am currently dual degrees computer science student. So we are going to discuss module 161 to 165. In these modules, we generally talk about pipeline and some analysis on the blocking. So let's start with the pipelining. So pipelining is just a kind of a different parallelization scheme for the affine loop nest. It is kind of different from the synchronization free or the sync based synchronization techniques that we have read so far. So, and also probably you have heard about the pipelining in the previous courses of computer architecture also. So we will just see the similar concept in at the compiler level also. We will try to implement the similar concept in the compiler side. So let's start with discussing from an example. So here we have a simple example. It's a two depth loop. It's a two depth loop which is executing xi equal to xi plus yji. If you glance at this loop, you can see that the outer loop is highly parallelizable, because for different ith iterations you are just writing to the particular xi element. So each ith iteration can be executed in different thread. But let's focus on YJI here. So let's say our YJI is load out in a row major form. So you can see that if it is load out in a row major form, then then the memory footprint is going to be very high, because we are accessing the columns of Y, and they are actually they have a larger you will have a larger memory footprint, and this will lead to cache misses. In our real case scenario, we are not going to use L1 cache, which is the most effective. Now, sometimes cache miss could be very expensive than parallelization, and it all depends upon the what a type of machine is. So let's say CPU. Let's say we consider this two CPU and a memory layout. So if a CPU 0 tries to access yj0, so we are just considering the simple parallelization where we have parallelized our outer loop. So each CPU is going to execute the ith iteration of this particular loop. So let's say CPU 0 access yj0 and CPU 1 is going to access yj1. So in here, both of the CPUs are going to have the cache misses, because this is not spatially local access, and each of these cache misses are going to be going to the memory. So if our memory is not if all these messes get serialized in the memory, then we are going to get larger executions time due to this. So to get more cache locality, let's just think about a scheme. So let's say each j thread or each CPU, let's just access the particular row of y. So it's going to access like yj0, yj1 or yj2, and also possibly it can write to x0, x1 and x2. So we can see this particular scheme. If this particular scheme can be implemented, then we can surely see that we are getting better cache usage and there is very high spatial locality in here. But there is one problem in here, that there is a data dependency. The data dependency is that each because each CPU J thread is going to write on the x0, x1 and so on. They are going, so each CPUs are going to access the x0 and they are going to write on that. So there is a data dependency here, but there is a catch here that let's say the CPU 0, when returned to x0, it doesn't need to reuse the value or need to access the x0 again. After writing to x0, it is kind of free and it is going to execute the other iterations. So let's just see in the more diagrammatic way. So as we have talked, so our particular CPU 0 is going to execute the particular is going to execute the jth element. So like the x0, so it is just going to is going to so here what we are doing is each CPU is going to run the inside iteration. So like you can see x0 plus equal to y00. So we are accessing yjth elements. So yj0, yj1, y00, y01, y02. For CPU1 we are accessing y10, y11 and y12. And what we want here is we want to just synchronize the access writing to the x0 in some way. So here what we will do is, after writing x0 to y00, the CPU 0 doesn't need the x0 here. So after writing to this, CPU1 can execute on x0, and CPU2, after CPU1 execute on x0, CPU2 can execute on x0. So this is the kind of this is what we are saying, the pipeline. This is what we say, the pipelining the accesses here. So in general, what is happening here is that so we have a so out in for each so each outer iteration is a task, let's say for now. And what we have done, for each task, we have divided it into the n stages. So each jth iteration is a stage. So and we have specialized each CPU to run on that particular stage. So CPU 0 is going to execute the stage 0. The stage 0 means it is executing with j equal to 0. CPU 1 is going to execute with j equal to 1. And what we are doing here is each iteration, so each so let here so the first iteration of CPU 0 is executing first, and after that the first iteration of the CPU 1 is going to execute here. So here it is so here we are just signaling the here we are signaling the next CPU here to execute after we have executed the previous CPU. So each CPU here is kind of specialized for that particular stage. And so this is kind of a very loose synchronization here. We are because we are just signaling the next CPU to start its execution, and the CPU 0 doesn't have to wait anywhere. It can start its execution and keep signaling the other CPUs. So here we have a ON synchronization here. What do we mean by ON synchronization? It means that we are actually needed n row and kind ON rows here to synchronize the writes to x0. and also like if you, and you can particularly see that this whole diagonal is a first task, this whole another whole diagonal is a second task, this whole diagonal is a third task, and each task each task are divided into stages, and each stages are pipelined here. So this is what the pipelining, this is what the pipelining is. So in general, in our computer architecture courses, what we have read is that each instruction, each add instruction or each subtraction instruction is divided into many stages like fetching, decoding, execute, memory, and write back. And our CPU is specialized for doing each of these stages. So in hardware level, we pipeline these processes in here. So each CPU has some five components which are specialized to do these five operations, and each instruction is divided in these five operations, and these five operations then pipelined in the hardware. So so in so in the compiler level, what we are doing is we are just specializing each task into the n stages. So here in hardware level it's fetch, decode, execute, and in our software level we are just taking it as a jth iteration. So pipelining requires the loop depth of greater than equal to 2, because after that what we can do is each iteration of outer loop can be counted as task, and the inner loop can be counted as stages, and after that we can just specialize each stage for the particular process. So let's take the more real world example, a real world example now. So we will talk about the SOR example. So it is successive over relaxation example. So this is the code. So here we are kind of averaging the xj plus 1th element by its neighbor. So it is kind of it is kind of a smoothing function that we used in the image processing also. So what we are doing is averaging the xj plus 1th element in this inner loop, and then we are just kind of averaging this xj plus 1 again and again by executing the outer loop. So we are kind of doing the relaxation of the values again and again. So here n is proportional to the size of x, and m here is proportional to the number of the relaxations. So before moving forward, let's talk about dependencies in here. So these arrows in this particular graph are all the dependencies here. So let's talk about the green ones first. So if you say any particular if you take any particular jth iteration, then for particular jth iteration you can see that we are going to write on xj plus 1 here. But if you consider j plus 1th iteration, we are going to read xj plus 1 from here. So here we are kind of getting read after write dependency here. So the green edge so we get this green edge because of that. Now the red edges are, you can see that the red edges here are actually dependencies on the xj plus 1 on different iteration, on different ith iteration. You can clearly see that in different ith iterations what we are doing is we are going to write on xj plus 1, and we are also reading the xj plus 1 here. So in between different ith iterations, we are going to get all the types of dependency here. It is var, is a var, raw, or var. We are getting all those type of dependency here. Now let's see the yellow ones. So in the yellow ones, what is happening is, let's take an example to understand it better. So here here at the 0 1 iteration, we actually are reading x1 here, and at 1 0 iteration we are going to write to x1 here. So this is kind of right after read dependency here. So we are getting these yellow edges everywhere in here. Now now the problem, now here you can see that this whole graph is kind of connected. So so if we try to, let's say we try to apply a sync free parallelism here, so you can see that if you take any 2 points, let's say we take this particular, so let's say we take this particular corner point and we try to take any other middle point, so we can see that these 2 points are dependent to each other. You can see there is a dependency, you can see there is a path from this particular point to the corner particular point. So these, so this whole 2 points are dependent, so we can't make any, so we can't make two different partitions which are kind of independent, independent with each other. So sync free parallelization is not possible here. So let's talk about the pipelining. So in pipelining, as what we have seen before is that we want to divide it into the task, and that each task has stages, and what we want is each stages of first task have a one-way dependency to the second task, and so on. And we want only one-way dependency. We want only one-way dependencies. We don't want any bidirectional dependency because it will just lose its purpose. And we want one-way dependency so that we can get a wavefront phenomena and we can do the pipelining. So let's try to do in this do the similar way as we have done before. So what we are doing is so each CPU is going to specialize on the particular jth iteration, and so like the CPU 0 is going to execute 0 0 1 0 2 0, CPU 1 is going to execute 0 1 1 1 2 1. So let's see. So this is our execution. This is how we are going to execute. But let's see how the dependencies here. So we know that zero. So we know that there is a dependency from 0 0 to 0 1. There 0 1, and their dependency to 1 to 1 0. So there is also a dependency from 1 0 to 1 1. So green dependencies. So these diagonals here are showing the green dependencies, but there is a depend so but there are the yellow dependencies also, which is bit from 0 1 to 1 0. So there, these are the zero dependence yellow dependencies, 0 1 to 1 0, 1 1 to 2 0. So this is a bidirectional dependency. So if we try to execute in this way, then we are not going to get the correct result, because 1 0 iteration needs the updated value from the 0 1 iteration. So we can see that dependence, so there are dependency between the stages also. So in they contain bidirectional dependency, so we can't do pipeline for this particular way. But if we see it diagonally, then there is a chance that we can do the pipelining. And why is it that? Because you can particularly see that each the dependencies are the one way here if we try to do it diagonally. So let's see how we can do this. So before moving forward, let's talk about the permutable loops. So till now, for one of the questions that we come in our mind is like how to distinguish between a pipelinable loop and a non-pipelinable loop. So first we talk about what is a permutable loop. A loop is a fully permutable loop if we can permute the iterations, if we can permute the levels of iterations without changing the meaning of the program. So in this particular is in this particular figure, so we have for ijk. So but we can but if this loop is fully permutable, then we can change it to jik or jki or any other combinations. Mathematically speaking, if there are two iterations, so if there are two iteration points I1 and I2, so I1 is actually equal to I comma j comma k. So if there are two iteration points, and iteration point 2 executes after the iteration point 1, and after permuting it, so let's say we consider this permutation, and after considering this permutation, let's say our I1th iteration execute after the I2 iteration. So if this is the kind of case, then we want then what we want is there should be no dependency between I1 and I1 and I2 in our case. So if we permuted our loop, then we don't want any dependency between those two particular iteration point, because if there is a dependency, then we are not going to get the same result. So so let's say the cases when we can consider our loop is fully permutable. So let's just take a simple case. We have a loop nest of depth 2. So here we have I and j, and we are just going to swap the axis to actually see whether it's permutable or not. So let's say you swap. So in the first case, let's say you swap the axis. So for the dependency edges that are between 0 and 90, so you can see that when you swap these x's, the execution order is going to remain same. So let's say you check 0 comma 0 and 2 comma 2, let's say. So when you swap the x's, the execution order is going to be same. So here consider the execution order is as we are going this in the zigzag manner, like from 0 1 to 0 2, and then 1 and all the way to here, and then 1 1 and 1 0 to 1 1 and all. So here the execution order between 2 comma 1 2 comma 2 and 0 comma 0 is going to be remain same. And also if you consider the 0 degree and the 90-degree edges, when you swap these x's, the execution order is same for them too. So so if we so if so we can clearly see that if our dependencies are between the 0 and 90-degree angle, then our loop is fully permutable. But if we take the dependency edges that are greater than that are generally greater than 90-degree, then in this particular case, if we try to swap the axis, then our execution order changes along this direction. So if the execution order changes here, then we if execution order is changing here, then we can't then this loop is not fully permittable because there is a dependency here. So let's say so if you particularly see 0 comma 1, and you can particularly see 0 comma 1 and like 1 comma 0 here. So if we change the our axis here, then the dependency, so we are just violating the dependency here. So what we want is particularly permutable loop, the data dependencies here generally goes from strictly lower I comma j to strictly higher values of I comma j, and the all the edges are going to be acute, all the dependency edges are acute here. So in this type of cases, our loop becomes permutable. So in our particular example, let's try to change the excel, try to change the angle of dependencies so that we can get our permutable loop. So we will use this particular transform where where our ith iteration is going to be same, and the jth iteration is the combination of I and j here. So after applying the Fortune-Morskin method and getting the bounds, we get this new loop. So for a particular ith iteration, the jth iteration go from I to I plus n, and then we do our smoothing operation here. So when you change the axis here, our data dependency graphs now looks like this. So now in this particular case, you can see all the dependencies here are now in the acute angle range. So we have get rid so all the dependencies that so these dependencies that were previously 135-degree are now become the 90 degree edges. So now we have got so now what we have got here, we got all the dependencies as the acute angle, and over this particular loop is now become the fully permutable loop. So now let's try to do pipelining in here. So what we do with the pipelining, that for each particular outer task, so each particular outer task I, we are going to divide each task into the n stages. So take a particular iteration I equal to 0. So this is our I equal to 0 iteration. So this is our first, this is kind of our first task, and each jth iteration is a stage. So j equal to 0 1 is stage, j equal to 1 is stage, and j equal to 2 is stage. So these are our stages in yellow. Now each CPU thread is going to specialize in this particular in these particular state in particular stages. So our task I so our task I for task I0 J0 is going to be executed by CPU1, J1 is going to execute by CPU1, J2 is executing going to execute by CPU2. So here this is how we have divided the task here. So now here also we are getting on synchronization because we have divided this particular loop into the n task. And so what will happen here is that for each particular, so for each task, so let's say you consider a particular task I. So for each task I, so what we are doing is, let's say this particular yellow line is the stage J. So for each particular task, so each particular task I, so the CPU J will wait. So CPU J will wait for this particular CPU J minus one to J minus one wait J minus one signal to execute before executing its iteration. So what I'm saying is the CPU this CPU particular CPU J has to wait for CPU J minus one to signal before the execution to signal before the execution. Yeah. So yeah, and also one of the things, so we have these boundary points here. So in these boundary points we, so let's say consider the left boundary here. So in these left boundaries, when the CPU reaches here, it doesn't have to wait for the previous CPU because there is no iteration point here for which CPU 0 is going to execute. So CPU 1 doesn't need to wait for this particular iteration to execute. So it can execute it straight away. Also for the right boundary, here the CPU doesn't need to signal the next CPU to start its execution here. So now, so after doing this, let's talk about the code generation in the pipeline case. So in general, if we have let's say k outermost fully permutable loops, and if we want to structure it as a pipeline, then what we get is we get OK minus one dimension with ON synchronization pipeline here. So if we take a particular SOR example, k equal to 2 here. So so because the inside loop goes for n iteration, so we have ON synchronization here, and because and the outer loops dimensions is 1 here, so we get the OM's task here. So OM task here. So OK minus 1 dimension defines the dimensionality of the tasks here. So yeah, so let's for now let's ignore the boundary conditions here. So if we ignore the boundary condition for now, so as you discussed just now, that particular processor P can execute state ith of a task only after processor P minus one executed the I minus one stage of that particular task. So to do this, we make the use of the construct called the condition variables. So what the condition variables do, they give the signals to start or stop the execution in general. So for every iteration, what the processor P is gonna do is processor P is gonna execute wait P minus one. So what wait P minus one is gonna do, the wait P minus one is going to wait for the signal of P minus one. Until then, it will wait it will wait for it before executing the body, and after the body, it will signal the P plus one to start its execution. So in the code form, so before going towards the code, so what we are doing here is that each so so to generate the code for the particular so to generate the code for the pipeline, what we are gonna do is we are going to specialize each CPU. So we are going to specialize, we are going to generate the code for each stage. So here we can see the JD value of JD here goes to go has a maximum value of m plus n here. So we need total CPU threads of m plus n plus 1. And what we are going to do, we are going to specialize the jth thread for particular state j. So for a particular state j, let's see let's see the values of I. It is going, let's see the values of I that we want. So we know the basic bounds here, that we know that I is greater than equal to 0 and I is less than equal to m. Now for particular value of j, so what we are doing is I is less than equal to j, and here I is greater than equal to j minus n. So if you particularly see this, if you see this loop particularly, then you see that the jd is starting from I, and it's increasing. So here I is particularly less than j, and because the upper bound on JD is I plus n, then just move the n here, then you get I greater than equal to j minus n. So after incorporating these inequalities, what we get is what we get our bounds as. So our starting bound of I comes max of 0 and the max of j minus n, and the upper bound becomes the min of j and min of j comma m. So now, this is the loop that is going to be executed for the particular CPU thread, and we don't need to do any change in the statement here. Now as we have talked, we are giving wait signal before the body of the loop, and we are giving j signal to the next processor after executing the body. Now, as we have discussed, as we have seen that left boundary nodes didn't need to give wait signal, and right boundary nodes didn't give to give to give the signal to next processor. So we know that left boundary is actually x equal to y. So whenever j is greater than I, it means our particular point is inside and it is not in the boundary. So we have to wait for the previous CPU. And also the same thing for the right boundary, that we don't need to, the right boundary comes in the x equal to comes equal to y equal to x plus n. So here when it is less, we don't need, when it is less, we need to give the signal, and when we are in the right boundary, we don't need to give the signal. So just to summarize here, we are we are we are generating the code for a particular state to specialize on that particular state. So this is the kind of specialization. This is this kind of the code generation, just specializing for the particular stage. So, so let's talk about after this. Let's talk about the difference between the pipelining and the barrier. So we know that the barriers have a log step semantics, which means that when we call the barrier in our code, then what will happen is that all CPU thread will reach the barrier, and they will wait till all the CPU threads have reached there, and after that they can start executing the next iteration. So what happens generally here is that some faster CPUs need to wait for more time for the slower threads, because after that only that lock is going to open when all the threads reach a particular stage. In the pipeline, there is just some level of asynchronous behavior here, is that the previous CPU have just to give signal to the next CPU, and after giving signal, it doesn't have to stop its execution. It can just it can still continue its execution. So it is kind of a relaxed wavefront that we are keep signaling the next CPU, and the execution is kind of moving forward. So in this particular type of case, if we have some CPUs that are faster or slower, then we can keep the fastest CPUs. We can keep the CPUs ahead. We can call them first. We can keep them the face of the execution, and after that we can call slower CPUs later, so that faster CPUs didn't need to wait for that CPU. So in here, one CPU can be slower, but there is a chance that other CPUs may not have to generally wait for it. So this is the great advantage for the pipelining in here. So this is here we have talked about the pipelining. Now we will move forward to some analysis on blocking. So first, so these we have. So let's consider a simple two level for loop, and it's executing some. It has some body here. For now, let's assume that there are no data dependencies here, and so if you see a particular execution, so this graph is particularly the execution order. So previously when we did blocking in the case of matrix multiplication, we talked about how we have seen that how blocking has helped in getting greater cache locality, that when we choose the particular value of b, we are able, so we choose a particular value of b so that we can fit that particular block in the cache. So if you do this if you try to do blocking on this particular two loop stage, so what we are going to, so this is generally, so we are just dividing this iteration space into the blocks, into the small blocks, and into the small blocks, and we are executing each block one by one. So now we know the benefits of the blocking, but let's now talk about like how compiler can detect it, and how compiler can detect it. So let's talk about like what are the conditions that on the S, what conditions should S follow so that we can do blocking in here. So let's see on that. So so one of the things here is that if you consider this example and you try to make a execution order here. So let's consider we have done the blocking of size 3 here. So so let's say we started the execution from 0 comma 0, and when we reach 0 comma 3 here, what we do is because we have done the blocking here, so the execution will return to this point, this point here, the point 1 comma 0, and then it goes to 1 comma 2, 1 comma 3, and then again here. And when we reach this corner point, the execution will then goes towards the will then goes toward the 0 comma 3 here, and then similar in this similar case, and then we reach this point again. So here you can see that at some levels the execution order has been changed. So for let's say for these 2 points the execution order has particularly not changed, but let's say just consider this the corner point of this first block and the starting point of this next block. You can particularly see in the left execution order, the 0 comma 3 point was executing first before the 1 comma 1 the before 1 2 comma 2 point, it was 1 comma 2 comma 2 point here. But in the blocking case, the 2 comma 2 here is getting executed first here. So we can see that the execution order is changing here. So let's see. So we know, because the relative order has been changed here, we don't want we don't want any dependency here, because as we have seen in previously many times, that if we have a data dependencies between these 2 points, then and if we change the relative order here, then we are not going to get the correct results. So if we consider a simple case like where the accesses to A are governed by some function of Bij, or the Bij, then we can't surely do the blocking in here, because we don't know how the accesses to Bij are going to go, and there would be higher chance of dependencies here also. So one of the things that we have realized is that if the order is going to change, if whenever the order is going to change in the blocking, then there should not be a dependency between them. So we don't want any dependency between them. So let's consider some of the points here. So these purple arrows are just to define the set of points here. So if we consider these 2 points, these 2 points are 0 comma 2 and 1 comma 3. So between these 2 points, the execution order hasn't changed. Similarly, between these 2 points, the execution order is not gonna change. So if you take the any particular acute angle set of points. So here acute angle set of points means that this arrow has is making the acute angle is making an acute angle. So you can see when you do the blocking, the execution order between them is not going to change. So so when you are so execution order between them is not going to change whenever you do any type of blocking here. So all the dependencies, so let's see if these are actually the dependencies. So so when we do blocking, these type of dependencies are not going to get violated. So the relative order remains same between these 2 points if we do the if we try to do blocking here. But let's say those points which make angle greater than 90 here. So let's say these two set of points make greater than they have an angle greater than 90. These 2 points have greater than 90. So so when you do the blocking, so in this particular case, you can see that between these 2 points, the relative order has been changed. So we can see that for the angle greater than 90, the execution order is changing here. But sometimes this execution order doesn't change. So if you can see that for the particular points, for the left corner point of the second block and this corner point of this third block, we can see that the angle between them is greater than 90, but the execution order between them is not changing before doing blocking and after doing blocking. So what we have seen is that the relative order there if the re- so what we can see from overall is that if there is a change in the relative order in the blocking, so whenever there is a change in the relative block in the change in the execution in the blocking, so whether you consider this point, whether you consider this point, there is likely that the theta is greater than 90 there. But whenever the theta is 90, we can't say that relative order change here. So for this particular case, we can't say the relative order change. But whenever the relative order changes in blocking, the theta is surely going to be greater than 90. So this gives us our sufficient condition that so what sufficient condition for doing the blocking is that whenever theta is greater than 90, we just don't take we just check whether there is we just want there should be no data dependency here. So it is kind of that we are not taking any risk, that when we are not going to take any risk for whether the theta is greater than 90, because the relative order can change for theta greater than 90. So to do the blocking, what we want is for whenever two set of points make have an angle greater than 90, we don't want any dependency between them. So so if you see this statement, then we have heard this statement probably in the permutable loops also, that about the acute dependencies. So 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 the permutable loops and the blocking generally share the same conditions only, that they don't want any dependencies that are greater than 90. So we can easily block the fully permutable loops. And in our matrix multiplication example, we actually did a three level blocking there. So in that particular matrix multiplication loop, if you see clearly, then the data dependencies on the Cij are going to happen only when the between the two iterations I1 is equal to I2, and the J1 is equal to J2. Only then we are going to get the dependencies. And this type of thing is not going to affect. This type of dependency is acute only if you try to make I comma if you try to see in a way like take any two different iteration points, and for that particular iteration points, the first condition is that I1 equal to I2, J1 equal to J2. Then for particular so then the data dependencies are just from lower values of k to the higher values of k. So this loop is fully permutable. So this loop is fully permutable. So this loop, the dependencies are acute here. And we also know that this loop is fully permutable here, because if you change any order in the, if you change any order in here, then we are going to get same result as we have discussed that because of the commutative property of addition. So we can successfully do the blocking in here, and we have seen how the blocking has given the great results in the matrix multiplication. So yeah, thank you. I think yeah, this is it.
Okay, thank you, Harsh, for that summary. Um, Great. So yeah, let's open the floor for questions. Yes, Jay.
Hi. So you mentioned in one of the lectures that we, I mean, right now we're just assuming that the plus is just a placeholder for some operation, and we are not using the properties that this operator has. So, uh, so I just wanted to ask, what kind of analysis can we do where we know some specific properties about some operators? Uh, like we haven't seen any like that before.
All right. So yeah, I mean, so far we have been talking about data dependencies, and based on that, we are basically figuring out whether we can pipeline. In fact, even before that, when we're talking about space partitioning constraints, whether we can parallelize, and also whether we can block. But if you use the properties of the operators, especially you know uh, one of the really kind of useful properties that people have used in the past are associativity and commutativity, and that's and they once if an operator is associative and commutative, like the plus operator is, then that's called a reduction operator, and the map reduce paradigm for doing computation is basically based on these kind of reduction operators. So if you know that it's a reduction operator, then you can basically choose to divide how you do it. For example, if you were to compute the sum of the first n elements and you had a parallel machine, so what you can do is you can kind of build a tree, and you can you can do pairwise sum for every first two elements, and three first you sum 1 and 2, then you sum 3 and 4, then you sum 5 and 6, and eventually you sum n minus 1 and n. And now at this next level of the tree you have n by 2 values, which are the sums of pairs. And now you can do the same thing again, and you end up with n by 4 values, and so on. And the total number of additions you will do there is going to be linear, but still going to it's going to be less, right? It's going to be, I think, n by 2 compared to n. And plus it's parallel. Yeah, the more important thing is that because each level in this hierarchy is parallel and the number of levels is only log n, if you have a highly parallel machine, you can basically do the sum of n elements in log n time, right? So that's basically so if now I'm using the example of plus as an operator that is both associative and commutative, but I can replace plus with some higher level expensive operator, very expensive operator that was also associative and commutative. And now I don't really need to worry about dependencies and stuff like that. I mean, just because of the operator's characteristics, I would be able to parallelize. So those are the kind of things we have not discussed. I mean, those are the kind of things we are not considering in this discussion. We're not assuming anything about the operator. And we're just saying, okay, let's look at only the data dependencies.
Okay. So, I mean, this might be a bit off topic, but so you said that I mean, we might have a big operator and we might save a lot in that case. Then, let's say I made some operator on my own, I defined some operator, and that is expensive. How would I let the compiler know that this is commutator or it has some particular property?
Okay, yeah. So so people have come up with all kinds of ways to do this. So you define an operator, And then, for example, your language can have extra modifiers, just like a language like C or C++ has modifiers that say, oh, this function is a const function, which means, it doesn't change the contents of that particular object or something like that. So you have a const modifier, or you have you have other types of modifiers like mutable and things like that. But basically, here also you can have a modifier for a function which says that this function is actually a commutative function, or it's an associative function, or it's a reduction function. And now if the programmer, and different languages will have different ways of dealing with this modifier. For example, a language one approach is that if the programmer has specified that it's commutative, the compiler can just assume it's commutative. It doesn't need to check whether it's actually commutative or not. Because the programmer's made a mistake, too bad. It's his or her fault. The other approach is, if this programmer has specified it's commutative, I will go and check whether it's actually commutative or not, and that's type checking. Right. So, and in some cases, it is possible to do type checking of that type. Right. So, by the way, there are real examples of such languages like MapReduce. I just use, there are more kind of these. Many of these languages are called data flow languages. Basically, you're dealing with a lot of data, and you have operators, and then these operators are kind of expensive operators. For example, the operator could be that compute the number of visitors on all my pages in the web, on my web service, which is spawning terabytes of data or logs or whatever, and that kind of thing. And then you say, oh, by the way, this operator is actually commutative and associative. And now, because of that, the compiler knows that, oh, I can just parallelize it in this way, and so on. And so MapReduce, it was after that there are more frameworks like Dryad, and there's also there are more such things. Apache Spark basically is another one which does in-memory kind of things. So there are all these kind of different programming models, and there are associated compilers that basically leverage this thing. Yeah.
Okay, thanks.
Okay. All right, Setu.
Hi. So I just wanted to ask one thing. So when we were talking about pipelining, and we were like we actually twisted the axis, we skewed the axis so that now it was more amenable to pipelining. I just wanted to know that this is not the only skewing operation we can do, right? We could have come up with a separate matrix as well, which would have worked. So this is not like a single solution. It's just one of the many solutions, right? I just wanted to confirm that, because when I was looking at the graph, so as of now, we brought J to the lower axis, right, to the x-axis. But if we were to, skew it the other way around, then in that case, I would have been on the lower axis, and then that would also have worked, right? So just wanted to confirm. Yeah. All right.
Absolutely. So yeah, there are many ways that you can kind of rotate or skew the axis so that you get what you want basically. And in this case, what you want is that all edges should become acute angles.
Yeah.
And there are many ways to do that, and there are many solutions. And I just showed you one solution. In fact, we haven't even discussed how that solution was arrived at. We just kind of assume that some oracle has given us that solution. And that's, we are not going into all the details of this particular algorithm. It's just, very, like, we have taken a high level understanding of what is involved, what kind of properties need to be checked, and how things would work. And then there are mathematical formulations, just like we had for space partitioning constraints. Given a program, there'll be a mathematical formulation. Then we'll need to solve that mathematical formulation, and out will pop a solution which would include this transformation matrix. And it could be, it could be the one that I showed. It could have been something else, but basically it's going to try to maximize the amount of parallelism even after pipelining, right? So minimum amount of synchronization, maximum amount of parallelization. And so yeah, there are multiple ways that you could potentially do it.
All right. Thank you.
So related to that, I have a question. So is it possible to change any program so that it becomes pipelinable, or are there limits?
I mean, so for one instance, let's say we have a completely sequential program. So let's say iteration I depends on iteration I minus 1. So I'm not sure. So even if I make it pipelinable, that would be like trivially not, it would not be really parallel, because the first CPU executes something, it signals the second one does something, the second one signals the third one. So would you
No,
call this pipelining or not?
like I'm looking at I'm looking at programs that have a depth of 2 at least,
Okay.
greater than equal. Right? I mean, that's the base condition of pipelining, right? I mean, you need to have a loop nest depth of at least 2. Yeah.
Okay.
We could have programs that have the index access is unknown at the compile time. That we may not be able to pipeline it.
Right, like the example that we had on ABIJ. Is that what you're talking
Yeah.
about? Exactly. I mean, but I mean, okay, that's one example where you've shown that it's so. By the way, yes, that's right, because in an in some, like if I have a program which has, let's say, something like a double dereference. So IJ basically gives you using IJ you dereference a location, and using that value that you got from that location you dereference another location, right? Use it in the address of the second location. And in that case, basically what happens is my dependency graph is like everything is dependent on everything. Like if I draw a graph, then if I draw dependencies, then 0, 0 is dependent on n, n, and n minus 1, n minus 1, and everything. Like everything has a dependency. It's like a clique, pretty much. And if it's a clique, then nothing can be done about it, right? I mean, then there's no pipelining opportunity here. Pretty much, you can rotate it any way which you like. It's going to be a clique, right? And it's a clique, so you won't be able to get like everything is a acute angle or something like that. But I think I need a more general characterization. That's one example, sure. But okay, so basically, in the example that we had, the SOAR example, I mean, the dependency edges were 135 degrees, and now we were able to change it. So now I could go one step further, and I could have made the angle to be, let's say, 155 degrees or something like that, then maybe 175 degrees, 178 degrees, whatever, right? And then all these cases seem like, oh, they can be handled. But there's a catch here. The catch here is that I'm assuming that, the gap, the distance between the from node and the to node is a constant. I mean, if it's a constant, then it's okay. But if it's something that's dependent on n, which is the number of iterations, then it becomes a problem, because then that angle is really kind of I mean, so obtuse. I mean, it's almost nearing 180, and that's I mean, even if you kind of rotate the axis, that's completely meaningless to basically I mean, there you won't get any pipelining out of that. First of all, the more obtuse the angle becomes, the more skewed your parallelogram becomes. The more skewed your parallelogram becomes, the less parallelism you have, because there's a lot of those kind of places where the amount of parallelism is going to be small, especially the corners and the points around the corners and things like that on both sides of the parallelogram. Also, if the angle is so skewed that it's actually coming all the way, I mean, it's coming that, I mean, sometimes if n was, for example, a symbolic constant, then you don't even know what is the, what is the angle, and in which case you won't be able to do that anyway. So yeah, I guess, the maximum for a 2D case, the maximum angle should have a bound, an upper bound on what it is, of course, and then you would be able to skew by that bound. And that bound should be kind of independent of the, I mean, it should be a small, it can't be, even if n was an actual constant, and but if the n was a constant like 1 million or something, then it doesn't help to basically, even though we theoretically we have a bound, but because of the skew that's going to get generated because of that transformation, the parallelism that you would get is not going to be worth the all the synchronization and all the yeah, all the synchronization, because there's a trade-off here. I mean, how much cost you pay for the synchronization versus how much parallelism you get, and so you don't want to skew the parallelogram so much that the synchronization costs dominate the parallelism benefits. Okay. Okay, I have another question. Okay, yeah, yes, question from Sayam.
For pipelining, do we implicitly assume that our memory model is a shared memory model because we have a different processor updating the same value or same memory location? So do we assume the shared memory model?
Okay, that's an interesting question. Do we assume, I mean, so far, by the way, we have been assuming a shared memory model, which means that there's a common address space across everybody. And we, of course, optimize for the caches and stuff like that, but we assume there's a shared memory model. Is it a necessity? I mean, I would actually throw back the question to the rest of the folks here. What do you think? Is it a necessity? I mean,
It's not a necessity. We just have to. There would be a lot of communication for sending the updated value for other processors in distributed.
right. Yeah, I mean, see, shared memory and distributed memory. There is a very nice, there's actually a one-to-one correspondence between shared memory and distributed memory system. Any operation that you do in shared memory can be mapped to an operation, equivalent operation in distributed memory, and vice versa. For example, a cache miss, that is basically like a message pass to the other thing. So you can be, and you can think of, I mean, you basically at a very coarse-grained level, you can think of all the CPUs as different actors, each of those caches as distributed memories, and then memory, the whole, which what you are calling the shared memory, is basically a third thing. And so shared memory is kind of, you think of, the way shared memory is implemented, it's just an abstraction layered over distributed memory. So at the hardware level, it's still kind of distributed memory, because these are all these kind of different actors, caches, memory, and they're kind of exchanging messages with each other all the time, right? And so at the hardware level, things are actually distributed memory. It's just that on top of that, to make programming easier, the hardware has basically layered an abstraction on top of it, which looks like a unified address space, right? And then you have to worry about all these things like cache locality, spatial locality, optimize for that. And when you're optimizing for that, you actually kind of now breaking that abstraction of unified address space, because now you're actually leveraging the fact that actually distributed memory, it's not shared memory. So I guess, the answer to your question is that no, it's not really dependent on shared memory or anything like that. Even though different processors are accessing X0, I mean, the same thing could actually in the hardware, it's going to be basically that, the message is going from the first processor. So let's say the first processor first updates X0. So what will happen is, let's say X0 will get cached into the first processor's L1. Then the second processor will access X0. What will happen is then X0 will have to travel from L1's cache to L2, from processor 1's L1 to processor 2's L1. Then processor 3 will access X0, and the same thing will happen. So actually it's message passing. Just that the hardware has hidden those messages from you. And even if the machine was message passing machine, which means even if the hard machine didn't implement the shared memory abstraction, you could do the same message passing in software.
So wouldn't it affect our performance a lot if each processor tries to update the same cache line?
Yeah, so I mean, absolutely. So, this is a trade-off between synchronization and parallelization. And question is, what is cheap, what is expensive? In certain situations, inter-cache messaging may be faster than cache misses all the way to memory. Example, the memory was remote or something like that, and all the caches were kind of local and things like that. So, I mean, as I kind of motivated right in the beginning of the discussion of pipelining, it all depends on the underlying hardware characteristics. And there are examples of underlying hardware where inter-cache communication will be pretty fast, but then going all the way, and because the caches are small, you'll sometimes have to go all the way to memory, and that's going to be pretty slow. And so that's what you optimize for in that case. Thanks for that question. Yeah, I think that brings clarity to the discussion. Yes, Pankaj.
So, sir, here I think we there are two parameters on which all this parallelization or pipelining is limited. One is one is the memory, and other is the CPU also. So, like here, as you had rightly said that let's move the faster CPUs on the left side and then slower on the right side, so that they don't have to wait a lot. So if all were slower, for example, then would we have to put some kind of buffer or something like buffer kind of situation there? Buffering maybe with, or or in this case, the wait time would be a lot and we could be okay with that.
Yeah. So by the way, I mean, all as in the previous question was about shared memory versus distributed memory, and I said that look, shared memory is just an abstraction. What's actually underneath everything is distributed, and there are messages being exchanged. Now you're saying that if the messages are getting exchanged, there are too many messages that are coming in, and the processor on the other side, the receiver is so slow. Then should there be a buffer? And the answer is, of course, yes. I mean, so now we are basically coming into like how to efficiently implement distributed memory system. And if you don't have a buffer, so how does hardware do it, by the way? The L1 caches, I mean, they do have like limited size buffers, maybe, small size buffers, so that, there's some amount of asynchrony that can be maintained. But then as you kind of make the buffers, firstly, having a buffer increases the circuit complexity, because now you have to, something is in the buffer, then you have to worry about, what about other, like if somebody tries to access it, now I have to also be able to serve from the buffer, right? Or something like that. So there, I mean, you kind of just exponentially increase your complexity with all this kind of stuff, especially with increasing buffer size and stuff like that. And so at some point, the engineers say that, okay, this is the limit of complexity that I'm going to allow. And then at that point, and if the buffer size, if the number of messages exceed the buffer size, then the sender needs to stall. And that would be a situation where the sender, the faster CPU may have to wait for the slower CPU. So you're right in saying that, it's not like, in pipelining, I basically, put all the faster CPUs in the beginning. And then, and it's not like, the faster CPU is necessarily going to finish all the time, because maybe the receiver is so slow that the receiver's buffer has become full. Maybe it doesn't even have a buffer. In which case the sender is trying to send a message and the sender is not getting, is not able to send a message. It can't get rid of the message. It doesn't have this asynchrony built into it, so it can move on. And so the sender gets stalled because the receiver is not going to receive the message. Yeah, so surely,
Okay.
yes. Yeah.
Thanks.
Sure. Okay, I wanted to kind of discuss what will happen in a higher dimensional case. So let's say I have a 3-dimensional loop. Then, in the code that I generated in the example that we used, we had a 2-dimensional thing, and like the CPU on the left is signaling the CPU on the right. And, we basically have this left-right thing. What about in a 3-dimensional case? In the three-dimensional case, what are the possibilities for the code generation, and what kind of, who will wait for whom? I mean, because, any thoughts on that?
So for three dimensional case, we can so assume there is a point in between. This is one iteration point, and then there is 6 points around it, right? Towards the left and right, towards top and bottom, towards the front and back. So for instance, if this is amenable to pipelining, maybe we are just passing the messages in the direction of the first quadrant, right? So towards I plus j plus k, this vector. So in the worst case, let's say the first this let's say some iteration point I is a dependency of all the iteration points in the first call. So in the first quadrant, so just the top one, the right one, and the front one, right? So in that case, the message would traverse from this point towards the first column, and it will the wavefront would be generated from a single point, and it would keep on expanding. But now it would be a surface instead of just being a single line, not line but a curve. Here.
Okay, thank you. Any other thoughts?
I mean, so the possibilities that I can think of is so we could have, let's say, the loopness depth is 3. So one possibility could be that I just have one-dimensional CPU space and I have two iterations, two nested loops inside that. Or the second possibility could be that I have a two-dimensional CPU space, and inside that I have a single loop that has an order in synchronization. I think these second.
Right. Yeah, exactly. Yeah. So yeah, thank you for both the answers actually. And so indeed, I mean, there are two possibilities in a three-dimensional case. One is that there's order n square synchronization and order n parallelism. And the second is there's order n square parallelism and there's order n synchronization. In the latter case, when there is order n synchronization and order n square parallelism, then they will have a wavefront which is like surface, which Setu said. In the other case, where there's order n square synchronization, the wavefront would still be like a linear, I mean, unidimensional thing. And in that case, basically, the code generated would also be very interesting because it will wait for two of its neighbors on each other's dimensions. So it's not just like just wait for my left. I'll probably say wait for the person on my left and wait for the person below me before I move forward, right? So you just have to kind of wait on both dimensions in that case. Right. So yeah, that's yeah. And then you can kind of take this to higher level dimensions and stuff like that. All right. Okay, so that's actually looks like there are no questions right now. So yeah, that's actually the end of our set of topics that we want to discuss for polyhedral analysis. And we're going to move to our next set of topics, which is about undefined behavior, both at the source programming language level and then at the intermediate representation level, and why they need to be different and things like that. Okay, so yeah.
Sir,
Question. Sure.
One question, right? So, sir, like we talked about this 3D kind of loop. So, if we keep increasing the depth, we can't keep going ever, right? For the parallelism. So, how do we limit that? Means like, where do we limit that, or what would be the factor to limit the amount of parallelism?
Sorry, can you repeat the
question? Like we have in this case 3 nested loops. So and then here we are saying like we have 2 possibilities like n square synchronization or n square parallelism. Now let's say if it was n dimensional, so then would it be n minus 1 parallelism and n minus 1 synchronization, 2 alternatives, or like we will what kind of alternatives we'll have there?
So for 3, we had 2 options. So in general, I guess the number of options would be n minus 1 options, right? I mean, basically, right. So for 4, it will be 3 options, I guess. And is that right? Yeah, I think so. Yes.
Yeah, seems like
Yeah, it seems like that. So yeah. So what's the question then?
So like, where do we can we have those many options to parallelize or?
Right. It depends on the dependency behavior of the program.
Right.
Whether a program that can be obviously like you want to parallelize it as you want to maximize the parallelism and minimize the synchronization.
Right.
So if there exists a solution that has n square parallelism, then that's the solution you should use. You shouldn't use a solution which has n parallelism and
Right.
n square. I mean, that would be suboptimal.
Right. 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 Thanks. Thanks.
Right. Let me switch off the recording and we can discuss some informal stuff.